7.26. This one's going to be a little different because we're actually going to prove something weaker than this problem statement. So, well, we're going to prove the conclusion using weaker assumptions, which makes the theorem stronger. And it is also going to take us a little more time, but, I mean, we get a stronger result. So, first, let's take care of this, the hypothesis cannot be admitted. For necessity of the norm of mu n going to the norm of mu, let mu n be delta n. Then certainly delta n is in mx. And we also know delta n goes to 0 vaguely. I think I discussed this in another exercise. If not, then it's not hard to prove. Also, the norm of phi n goes to 1 because each delta n delta n, the delta n measure of the whole space is just 1 because the point n is in the space. This is, of course, the measure that here we're taking x to be r, or x to be c, but x to be r is fine. So this goes to 1, and 1 is not 0. So it does, and 0, of course, is the measure of the space with respect to the 0 measure. So let's see here. Oh, so phi n does not go to, or delta n does not go to the norm of delta, or here, which is not 0, which is equal to the norm of 0, right? Where this 0 here is the 0 measure, and this 0 here is the number 0. So then what we want to prove is that it's not the case that integral of f d mu n goes to integral of f d mu for every f in bounded continuous functions. Then if f is identically equal to 1, then certainly f is in bounded continuous functions on, we'll say, R, but integral of f d delta n equals 1, because n is always in, because what this is you just take whatever f is at n, and f evaluated at n is what it is everywhere, which is 1. So this is 1, and so this converges to 1, which is not 0, which is the integral of f with respect to the 0 measure. Okay, to prove the desired claim, we will define a sequence mu n in mx to be tight if for all epsilon greater than 0 there is a compact set K such that for all natural numbers n, the total variation of x set minus k with respect to mu n is less than epsilon. Now note that each of these measures mu n is a Redon measure, and so for every particular n you can already find, because the measure of the space is finite, you can use an irregularity to get such a compact set K for every fixed n. So what this tightness tells us is that we have uniformity in this choice. So I claim that under the assumptions given in the problem, the sequence mu n is tight. I'm not sure if this is a standard definition, but it'll work for this problem. So to prove this, we're going to do the standard thing, let epsilon be greater than 0. Then there is some f in C0x such that the uniform norm of f is less than or equal to 1, and the integral of f d mu is greater than the measure of the whole space minus epsilon. And why is that? That's just one of the That's because what you can do is you can just basically do irregularity. This is basically very similar to this fact over here that you can do this, but you do irregularity to choose a k such that if you wanted to do this more concretely, you could choose a k such that this statement here holds, and then what you could do is you can define a function f to be 1 on this set k, and then vanishing at infinity, which you can do by like your zone or something. You could probably get it to be cc even. Whatever. This you can always find an f such that this holds. So thus, well, not always, but in this scenario you can. So thus, what do we have? Hold on. Thus, mu, the total variation of mu, if you just rearrange this a little, you get this is less than epsilon. So then by vague convergence, and since norm of mu n goes to norm of mu, there exists some n and n such that for all n greater than or equal to n, see here, mu n minus integral of f d mu n is less than 2 epsilon. That's because we can approximate norm mu by norm mu n, and we can approximate integral f d mu by integral f d mu n, since f is in C0. And so you need to put in some epsilon, so we'll just use this in epsilon over 2. And basically for this particular capital N, we could choose like a separate n for each of these different things, and then you choose capital N to be the max of those two that you choose, one for mu n here and one for mu n here. But anyway, so you can do this. For each natural number n, we have a computation that I'm not going to fit, but let's just start it. Let's take the integral 1 minus f d, then absolute value of mu n. Let's see here. My screen. Okay, so what is this? This is less than or equal to, we're going to add and subtract the integral of f d mu n. So let's add it, integral of norm f d. So this is absolute value of, here, I'll try to write this a little better. Oh, I was f d mu n. I had a compile error missing right, but this is fine now. So plus integral f d and then mu n, and then we're going to subtract it as well. But when we subtract it, we're going to get a less than or equal to here and bring the integral or the absolute values outside. And this is because we know that the absolute value of integral of f d mu n is less than or equal to integral of norm f d total variation of mu n. And so putting on the minuses just flips the inequality. So we get this, and what do we do with this? This is equal to, well, this and this cancel out, so we just get the integral of 1 d mu n, but that's just the total variation of mu n. Well, the measure of the whole or the norm of mu n, and then this minus f d mu n stays here. Oh, but does this look familiar? This is exactly what we had up here, except it's not quite. No, it is quite. This is the 2 epsilon thing. Okay, so hence, for each n greater than or equal to n, integral of 1 minus norm f d mu n is less than 2 epsilon. So now we're going to let k1 be the set f is greater than or equal to 1/2. Then what do we know about K1? K1 is compact. And why is that? That is because if you look at norm F, F is in C0, and what it means to be in C0 is precisely that for every epsilon, the set where the norm of F is greater than or equal to epsilon is compact. So we know that K1 is compact, and x set minus k1 is equal to the set where f is less than 1/2, and if we just do some subtracting, we get 1 minus f is greater than 1/2. Am I missing? I think I'm missing absolute values here. I'm either missing absolute values here or the absolute values definitely matter here. So 1 minus norm of f, right, because you take 1 minus norm of f is greater than minus 1/2 here, and then you get norm f minus, oh wait, that's weird. No. Right, because 1 minus 1/2 is positive 1/2, and so 1 minus norm f is greater than 1/2. So there you go. Yeah, this is good. So now what? So by Markov's inequality, and that's something you have to remember, for each n greater than or equal to n, norm mu n of x minus k1, which is precisely the measure of the set where, that's precisely the measure of this set, is less than or equal to 1 over this constant that we have in here times the integral of 1 minus norm f d norm mu n. And that's precisely what Markov's inequality says. If you just replace the x minus k1 with this thing, then it just works out. But this is just what we had before, but we've got this 1 over 1/2, so this is less than 4 epsilon. By replacing k1 by a larger compact set k, we can ensure that mu n x minus k is less than 4 epsilon for all n and n. And why can we do this? Well, first of all, note that this thing that we had before was just for sufficiently large n. It was only, we only had this less than 4 epsilon. This only held for n greater than or equal to this capital N that we chose. So we want to make this true for all n, and remember that we get this individually for each particular n here, just because these are Radon measures. And so what you can do is, because we've basically taken care of the tail of this the sequence of mu n's with this estimate, and so then all you have to do is you have to take into account the first number of them, but for each of them there's just finitely many, and for each one you choose a compact set that does exactly what you want it to, and then you can just take the union of the compact sets, which is then going to be a compact set because it's a finite union of compact sets. And so then that's going to satisfy what you want. And so hence, mu n is tight. So I now claim that if mu n is a subset of mx, mu n goes to mu vaguely, and mu n is tight, then integral of f d mu n goes to integral of f d mu for all f in bounded continuous functions on x. So this is why our result is stronger. This is because we're saying that if all we need is this to be an mx to converge vaguely and for the sequence to be tight, and then we get the same conclusion. Now the assumptions that we had previously were that mu n were in mx, mu n goes to mu vaguely, and instead of this tight condition we had norm mu n goes to norm mu. And that certainly, and we just proved that that implies, that combined with these other assumptions implies that the sequence is tight. And by the way, we did need those other assumptions, like we did need to use that mu n goes to mu vaguely when we chose, when we did this argument involving integral of f d mu n. So I can't think of anything off the top of my head, but I think there are examples where you can have, where this actually gives you something stronger. Basically, you can have a sequence that's mu n is in mx, mu n goes to mu vaguely, mu n is tight, but now that I think about it, we did prove that you need the norm of mu n to go norm of mu. Oh, but that sequence wasn't tight. So maybe it's enough to have tightness. And there are sequences which are tight, but such that the norm of mu n does not converge to the norm of mu, but you still get this conclusion that this convergence happens for all f in bounded continuous functions on x. So I don't know of any examples right now, but I'm pretty sure what we're proving is not only like greater than or equal to the Folland problem in terms of strength, I think it's strictly stronger. But anyways, let's actually prove the problem now. So if this is tight, then this converges for all f in bounded continuous functions. So let f be a bounded continuous function on x. Let m be some positive number such that norm f is less than or equal to m, because f is a bounded function, so we can bound it by something. So let epsilon be greater than 0. See here. By tightness, we can choose K1 a compact set such that for all n and n, natural numbers, not written horribly, norm of mu n of x minus k1 is less than epsilon over 3m. So this is going to be an epsilon over 3 argument. Since mu is Radon, choose K compact such that K contains K1 and mu of x minus K is less than epsilon over 3m. For example, you could choose a K that works just for this particular mu by Radonness, and then take the union of that compact set with K1. And this is useful because now this not only is mu of x set minus K less than epsilon over 3m, but same thing holds for mu n. Now by Eurozone, choose some CC function g such that g equals f on k. By vague convergence, choose a natural number n. Come on, computer, we're almost done with this problem, don't die on me. Large enough that for all n greater than or equal to n, the integral of g d mu n minus the integral of g d mu is less than epsilon over 3. Then for all n greater than or equal to n, now we do our estimate. Integral of f d mu n minus integral of f d mu. And what do we know? We know stuff about this compact set k, so let's break stuff up like that. Integral of k x minus k, set minus k, f d mu n, minus integral of k f d mu, minus integral of x set minus k, f d mu. This is going to be less than or equal to, we combine the things that are defined on k, then we add, we're going to bring the, we're going to use this inequality to bring stuff even further inside, so we're going to make this norm f d mu n plus, and we're going to make that, this is d mu n, the mu n is a norm, or the total variation of mu n, plus this d norm of mu, and then this is going to be less than or equal to, can I fit it on this line? Integral over k of g d mu n minus integral of k of g d mu. And that's because g equals f on k by construction. So we can make that substitution. And of course we were able to do this vague convergence thing here because g is a CC function. In fact, C0 would have been enough. Yeah, sure, let's do that. Certainly we can do it. If you wanted it to be CC, you could do that by using an outer regularity argument on the compact set K, but whatever, this is fine. So this plus, and then what are these things going to become? We're going to get this norm f, we're just going to pull that out and estimate that by the bound m, times the total variation mu n of x set minus k, and we're going to do the same thing mu x minus k. Now we chose n such that this term was less than epsilon over 3. N such that this term is less than epsilon over 3, and these two terms are less than epsilon over 3m, and the m's are going to cancel with these constants that we got here, so this is just less than or equal to epsilon. Hence, for all f in BCX, let's see here. So for all n greater than or equal to n, so let's just write this out. So integral of f d mu n goes to integral of f d mu. Hence, for all f in BC of x, integral of f d mu n goes to integral of f d mu. And there we go. We've completed the proof.